Hello, I'm Luis Serrano, and this is Serrano Academy, and this video is about how to tell distributions apart. Average, variance, skewness, and kurtosis. These are four measures that will tell us a lot of information about a distribution. This video is in collaboration with Deeplearning.ai, and it's actually part of a course of the 3-course specialization on mathematics for machine learning that we built together. I will tell you more about the course later, but let's get started. So first, we're going to talk about the average. And I like to see the average as what is the price that I should pay for a game. What game? Well, let's say we're tossing a coin, a fair coin. So it's a 50-50 heads or tails chance. And if it lands in heads, then let's say you win $1. And if it lands in tails, you win $3. And the question is, to make this game fair, how much should you pay to play it? So you probably have a number in your mind, but let's actually do the math. So since it's 50-50 chance, we're going to put a 0.5 and 0.5 kilogram weights at positions $1 and $3. And the question is, where would this balance? This is the price that you should be paying. And it balances in the very middle at 2 because the average is 1 plus 3 divided by 2, which is 2. You can also see it as $1 times the probability of heads, which is 50%, plus $3 times the probability of tails, which is another 50%. Or graphically like this, $1 times 0.5 plus $3 times 0.5, which is 2. So that we're going to call it mu. Normally, mu is the letter for the average, the Greek letter mu, and it has many names. It can be called the expectation, it can be called the expected value, the average, the mean, or many other things. We're going to call it average today, but just keep in mind that it can be many things. So now let's complicate the game a little bit. Now you are rolling one die. So there are 6 possibilities. And let's say that if you hit 6, then you win $12. And otherwise, you win 0. So what is the price for this game? I invite you to pause the video and think about it. And I'll tell you, let's do it again. Let's put a 1/6 of a kilogram in $12 and then 5/6 at 0 and see where this balances. And it balances at 2 because 2 is the price you should be paying. Why 2? Because we calculate the average 0 plus 0 5 times for 1, 2, 3, 4, 5, and at 12 for the value 6, and then divided by the total possibilities, which is 6. Or we can also write it as 0 times the probability of 1 or 2 or 3 or 4 or 5, plus 12 times the probability of 6. So the probability of winning times how much you won, add all those, and you get the expected value or the average. It can also be seen like this graphically, and that is equal to 2. So we have our first formula. The average is going to be 1 over n times x1 plus x2 plus all the way to xn. And remember, we can also call it the expected value. That's going to be the expected value of the variable x. X is our random variable. And to make this even more clear, let's put ones on the exponents. So we have e of x to the 1 is the average of x1 to the 1 plus x2 to the 1 plus all the way to xn to the 1. Why am I having that exponent 1? You'll see. Now, if we have a continuous variable where we could pick any of these values with the likelihood equal to the height, the same thing happens. The average or the mean or the expected value is the place where you would balance this distribution. And since it's a continuous variable, if you like integrals, the formula is this one over here. If you don't like integrals, just think of it as an infinite sum of tiny things. Or you can think of it as, where would I balance this mass over here? Now, something very important is that we always need to center your data. If you're doing data science, statistics, machine learning, it's always important to center your data. What does that mean? Well, I have my distribution here with expected value mu equals 2, and I would like that to be 0. So I'm just going to subtract 2 from everything and move it to the left. And I get that now you pay 0 for the game. It's the same game, but instead of paying 2, you pay 0. And 5/6 of the time you lose $2 and 1/6 of the time you make $10. It's the same thing as paying 2 and making 0 or 12 because I just subtracted 2 to everything, but it's the same game. And so in general, we're going to do this to handle our data better. What does that mean? We went from a random variable x to the new random variable x minus mu. So always good to do that. If you have your variable x, you calculate the mu is the mean, and then you'd have a new variable x minus mu, and that one is centered. It has an average of 0, and then the math is just a lot simpler. We'll see. Okay, so now that we know the average, let's go for the next one, which is the variance. The variance tells me how risky is a game. So let's play a similar game. Now you still toss a 50-50 coin, except that now it's centered. So the game is free. Sometimes you win, sometimes you lose. And it goes like this. If it's heads, you win $1. If it's tails, you lose $1. So again, it costs nothing to play because it's centered. Now you have another game, game 2. In game 2, if the coin lands in heads, still 50-50 chance, you win 100. And if it's tails, you lose 100. So question for you, which game is riskier? Well, it's clear that both are fair games, but the second one is riskier because yes, you may win $100, but you may lose $100. It's just, you have to think about it a lot more. But the average is the same because if you look at this one, the average is 0. And if you look at this one over here, the average is again 0 because it's 100 minus 100 divided by 2. So now the question is, how do we tell these two games apart if they have the same average? Well, as you can see, the riskier the game is, the wider it is because the first game is pretty narrow and the second game is pretty wide. So what we have to do is we have to measure the width, and that is associated to the risk of the game. So how do we measure the width? Well, let's do some numbers. Let's do it for the first one. We look at the center, which is 0 because we've centered it, and there's a distance of 1 in one direction and 1 in another direction. So these distances are 0 minus 1 and 1 minus 0 because 0 is the point in the middle, and then there's a 1 on one side and a minus 1 on the other side. However, if I add those two things, I get 0. So that doesn't work so well. So it looks like I have to make them both positive because I have a 1 in one direction and a minus 1 in the other direction. So what could I do? Well, one thing I could do is to add absolute values. However, I prefer not to because absolute values give us this corner in the bottom. It's hard to differentiate. It's more of a complicated function. On the other hand, there's a better function that turns everything into positive, which is squaring. What I'm going to do is I'm going to square those two numbers. Squaring might be more complicated, but it's nice because it's differentiable everywhere. It's a nice parabola. So we're almost always going to pick a square. And now I take the average of those two squares, which geometrically looks like if I did a square on top of that distance and I looked at the area, and I take the average of those just like before. So 0.5, because the weights and the probabilities there are 0.5, multiplied by 0 minus 1 squared, which is 1, and by 1 minus 0 squared, which is 1. And so we get a 1. That's going to be the variance. And as you can see, it's associated to the width, because let's take a look at this other one and see what we get. So we have a distance of 100 here and 100 here. Obviously, they are 0 minus 100 and 100 minus 0, because the 100 is here, the 0 is here, and the minus 100 is all the way there. So now I'm taking the average of these two squares over here, which is much bigger. When I do the math, I get 10,000, because it's 0 minus 100 squared, that's 10,000 times a half, plus another 10,000 times a half. So we get 10,000, which is much bigger than 1. So in general, the formula is going to be the average of the xi squares. So it's the expected value of the square of the variable. Before we had it to the power of 1, now we have it to the power of 2. And so a small recap, we had the first moment. We're going to call this the first moment. That's the average, the expected value of x to the power of 1. And the second moment is going to be what we just learned, the variance, which is the average of the xi square, the expected value of the square of the variable. And that's going to be the variance of x. And so if the first one tells us about the price of the game, the second one is going to tell us how risky the game is. Now, there's a small detail I'm leaving out. The actual formula for variance is this. You have to do expected value of x minus mu squared, where mu is the average, this one over here. However, as I told you, if you always center your data, if you always take your variable and subtract mu, and now you have one where the average is 0, then the variance is much easier. It's expected value of x squared, not of x minus mu squared. So in general, it's always a good thing to center your data. Math becomes simpler that way. Now, as you see, we have the first moment and the second moment. Obviously, more moments are coming up, but before that, I'm going to tell you what happens with a continuous variable. So let's say we have this one over here with small variance and this one over here with large variance. As you can see, the one with small variance is narrower. You have more control over a random number that you pick out of that distribution. This one is much riskier because you could get a number that's really high or really low. So again, in a continuous variable, the width is measured by the variance. And the formula, again, if you like integrals, is this one over here. It's just the integral of x squared dx from minus infinity to infinity. And so that's the variance. And one more thing we want to do, remember I told you to center your data, you also want to scale your data. Take a look at this. The first game has a variance of 10,000, and that's actually too big to handle. We can actually scale our data and have a smaller variable and still keep all the information. So what we would do is take the data and now scale it so that it has a variance of 1. So we bring it all down to the center. The second game, if you remember, has a variance of 1. So what do we do to scale the data? Well, what we do is we take our variable x and we divide it by sigma. What is sigma? Sigma is the square root of the variance. So if you take your data after you center it and then you calculate the variance and divide every single point by the square root of the variance, then you get nice centered and scaled data which has an average of 0 and a variance of 1. And it still keeps your information, but in a much nicer and compact way, and then the math is easier. So for example, for this case, we're dividing by 100 because 100 is the square root of the variance, which is 10,000. So now that we learned average and variance, the next thing comes up, which is the skewness. The skewness tells us if our game looks like an insurance or like a lottery. What do we mean by that? Well, we're going to change a little bit, and now we're going to play the roulette. So the roulette is basically picking a random number from, let's say, 0 to something, and then if we pick the right number, then we win a lot of money, and if not, we lose some money, which is the money that we bet. So in this case, let's say we pick a number from 1 to 100, and they all have the same probability. It's uniform. And we're going to play the game of lottery. So if the number we picked, let's say it's 100. 100 is the winning number. So if we hit 100, then we win $99. And if it's any other number, we lose 1, which is the ticket for the game, or how much we bet at the roulette. So we lose $1 or we gain 99. Notice that that's the same as if we won nothing and gained 100 and the game cost 1, but I centered it. So the game is free, but then you lose $1 or you win 99. So that's one game. Now pay attention to the second scenario, which is similar but different. In this more unfortunate game, you have insurance for your car, but you decided not to buy insurance for the car, and that's kind of like playing the lottery. Now, what happens if you don't buy insurance for your car? Well, let's say the probability of crashing is 1 over 100. So it's the same as playing the roulette, except it's the opposite, because if it hit that lucky, now unlucky, number of 100, you're going to lose $99 because you have to repair the car yourself. But otherwise, if you don't crash with the probability is 99 over 100, then you win 1 because you didn't spend that dollar that you paid for insurance. So if you didn't crash, you're good, you won. And if you were unfortunate and you crashed, then you lost a lot of money. So as you can see, these two games have almost the same math except flipped. In one, if you're lucky, you win a lot, and otherwise you lose a little bit. And in the second one, if you're unlucky, you lose a lot, but if you're lucky, you win a little bit. So how does that look? Well, on the one on the right, you have 99% probability of losing 1, which is buying the ticket and not winning the lottery, and 1% probability of winning $99, which is if you win the lottery. And the other one is the other way around, because you have a 99% probability of winning $1, which is if you don't crash and you didn't have your insurance. But unfortunately, you have a 1% probability of losing $99, because if you crash and you didn't have insurance, then that's a problem. So how do we tell these two games apart? Well, they have different skewness. They're skewed in different directions. The first one has most of its weight very close to the left and a very, very, very far weight to the right. And the second one is the opposite. Everything is to the right and a really, really, really far away small weight to the left. So they're skewed in different directions. So now we need to be able to tell these two games apart. Let's see if the average or the variance can help us. Unfortunately, they don't. They have the exact same average. If you calculate the average, both games are centered at 0, because 0.01 times minus 99 plus 0.99 times 1 is 0, and that expression there is also 0. So same average. Now let's look at the variance. What happens with the variance? Well, they still have the same variance, because if I were to calculate this expression, it's the exact same thing as that expression, because the negatives become positives when I square. So we get the exact same variance, which makes sense because both distributions have the exact same width. They're flipped, but they have the exact same width. So the risk is the same. So what can we do? Well, we have an exponent of 1 here and an exponent of 2 here. Why don't we try an exponent of 3? That is going to be the skewness. So when we calculate the skewness, we get this expression for one game and this expression for the other game. So now I take the average of the cubes. And now the cubes don't have that problem that the squares have, that turn everything positive. The cubes still turn things negative when they're negative. And moreover, this 99 cube becomes something really big, so it eclipses this 1 here. So it actually captures where your far away data is. It's much more sensitive to points that are far away. See, the average puts this and this in the same balance, but the moment you take a cube, that 99 cube goes way, way, way to the right, so it captures the skewness. And the value we get for the skewness is 9,702 for the lottery game and negative 9,702 for the insurance game. Now I kind of lied to you because I didn't center this data. So what we have to do is calculate this variance over here, take the square root, divide, and then calculate the skewness. So I don't exactly know the number, but it's going to be positive something over there and negative something over here. So they're different because one is positively skewed and the other one is negatively skewed. So I invite you to do that math of dividing by the variance by yourself. But I assure you, you're going to get some big number and the negative of that big number as the skewness. So now we have the third moment, because we have the first moment is the average, the second moment is the variance, and the third moment is the skewness, the average of the cubes. And of course, what I really meant is expected value of x minus mu, the average, divided by sigma, the standard deviation, which is the square root of the variance, and then cube that and take the expected value, where again, sigma is the square root of the variance. But if we center our data and we scale it, then it's just this simple formula over here. And now for a continuous variable, it's just going to be the integral of x cubed from minus infinity to infinity divided by n. And you're going to have some distributions like that with are negatively skewed, where there's points way, way, way far to the left. We're going to have some positively skewed when they're going to be points way, way, way far to the right. And something like this is not skewed like the one over here because it's kind of centered. So the skewness is very sensitive and it actually captures where is your data pointing when the average and the standard deviation or the variance cannot capture that. So we're almost done. We have one more measure, which is the most sensitive one, which is kurtosis. Kurtosis tells us if the risk is controlled or not. What do I mean by that? Well, again, let's have two similar games. The first game is similar to the ones we've seen before. If you toss a fair coin and if it hits heads, then you win 2. And if it hits tails, you lose 2. And the second game is less risky because in this one, I don't have to toss a coin, or if I want, I toss a coin. But the fact is you always win $0. If it's heads, you win 0. If it's tails, you win 0. This is the least risky game in the universe because you're not doing anything. So obviously, the first game is riskier than the second one. And this is the balance for the first game, which is at 2 and at minus 2, I have weights or probabilities of 0.5. And in the second game is very simple. I just have a big weight of 1 at 0. So the variance here is 0. And the variance for the one at the top, just like before, I have my plus 2 and my minus 2. I square them and then I average that out and I get 4, because it's half of 2 squared plus half of minus 2 squared, that's 4. So again, the first game is obviously riskier and I've done nothing so far, but let me try to make the second one just a little more interesting. We're going to keep the first one as it is, and the second one is going to be like this. Most of the time you win 0. So 96% of the time you win 0. You can think of it as picking a number from 1 to 100, and if it hits from 1 to 96, nothing happened. But with a small 2% probability, you would win $10. And with a small 2% probability, you would lose $10. So most of the time nothing happens, but if you hit this little region here, you can win or lose a lot. So how risky is that game? Which of the two games do you think is riskier? I invite you to pause the video and actually calculate it, and you may get a surprise. But let's see how the balance looks like. I have a huge weight of 0.96 of a kilogram at the very middle. I have a tiny weight of 0.02 way over there at the left. And then I have a tiny weight over here of 0.02 at 10. And again, this game is going to balance at 0 because it's fully symmetric. So now the question is, which one is riskier? Well, we'll calculate it pretty soon, but if you take a look at it, the first one looks like a controlled risk. I have risks, but I know that at the very most, I will lose $2 and I will gain $2. So it's controlled risk. The second one is mostly steady because most of the time there's absolutely no risk. However, there are 2 surprises that could happen. It could go crazy on either direction with a small probability. So I'm going to call them control risk and steady with surprises. Now let's see if the variance can tell us if you have a control risk or if you have a steady with surprises. Well, the variance for the first one, we calculated it and it's 4. What's the variance of the second game? Well, let's calculate it. I have a 0 squared, I have a minus 10 and a plus 10, and I'm going to take the average. So it's 0 times 96% plus minus 10 squared times 0.02 plus 10 squared times 0.02. And what does that average amount to? Well, unfortunately, when you calculate that, you get 4. So we got the exact same variance for both games. Variance tells us the risk of the game, but it's not sensitive enough to tell us if we have a control risk or a steady game with surprises. So what can we do? Well, now we have to go to the next moment. So let's take a small summary. These two games have the exact same average. If you calculate the average, they're both centered at 0. They have the exact same variance because we've calculated both variances. So they're just equally wide except in a weird way. I invite you to calculate the skewness and you will notice that is the exact same thing. It's going to be 0 because you don't have skewness towards the right or towards the left. They're both centered. When something is fully centered, you have skewness equals 0. So the next thing we can calculate is called the kurtosis, and the kurtosis is what you would expect. You have exponents of 1, 2, and 3. It's just going to be an exponent of 4. Let's see what happens. When we calculate the average of x to the 4, then we're taking the average of 16 and 16, which is 16. So the kurtosis of that one is 16, is the average of the variable raised to the power of 4. Now, what's the kurtosis going to be here? Well, let's calculate it. We're going to have this number over here, 0.96 times 0 to the 4, 0.02 times minus 10 to the 4, and 0.02 times 10 to the 4. As you may guess, it's going to be a lot bigger because 10 to the 4 is huge. This is going to be 400. And 400 is a lot bigger than 16, so the kurtosis is bigger for a steady with surprises than it is for a controlled risk. And why is that so big? Well, take a look at that width. You have a 2. To the 4 is 16. On the other hand, for the second one, you have a width of 10. And 10 to the 4 is huge. It's 10,000. So 2 and 10 may be similar. And so the variance square them and is not going to get such a big difference. But when you raise them to the 4, the 2 becomes a 16. The 10 becomes a 10,000. In other words, if I have a tiny weight really far away, I take that distance raised to the power of 4. So that distance all of a sudden speaks really loudly. And even if the weight is small, if the probability is small, the fact that that distance is so big, you raise it to the 4, it just rings a huge bell. So in summary, the control risk has a small kurtosis and the steady with surprises has a big kurtosis, even if they have the same variance. Now again, my data is centered because the average is 0, but the variance is 4, it's not 1, so I actually didn't scale it. If you want to calculate the actual kurtosis, you would have to divide the data by 2, which is the square root of 4, and then calculate it. But you get the point. It's a lot bigger here than here. And so here we have our 4 moments: the average, the variance, the skewness, and the kurtosis. And of course, here I am centering my data. If I didn't want to center it, then I would have to do expected value of x minus mu divided by sigma raised to the power of 4. And for a continuous variable, kurtosis basically says the following. If I have these two variables and they have the same variance, if I calculate the variance, they have the same variance except they look different. Well, if most of my data is centered, even if it's not that centered, even if it's kind of wide, it's mostly centered, then I have a low kurtosis. But if I have a variable that is even more centered, but it has surprises on the sides, the little bumps far away from the center that still don't make the variance that big, they will make the kurtosis really big. So that's controlled risk, and this is steady with surprises. And the formula is just like before, except now you take the integral of x to the 4. This is for a continuous variable. So for a discrete variable, you take the sum and divide by n. Here, you take the integral and divide by n. So a small summary, we have these 4 things. The average tells you where you can center your data, where you can put it and balance it as if it were a weight. That's expected value of x to the power of 1. The variance tells you if it's wide or if it's narrow. So low if it's narrow, high if it's wide, if it's more risky, and it's the expected value of the square of the variable. The skewness tells you if it's skewed towards the right or towards the left. It's negative if these values are at the left and positive if they're at the right. And it's e of x to the 3, so expected value of x cubed. And then kurtosis tells you if you have a controlled risk or if you have a perhaps steadier variable but with some surprises on the sides. And the formula for kurtosis is e of x to the 4, the expected value of the 4th power of the variable. So now in your toolkit as a data scientist or as a statistician, you have 4 more tools that can tell you a lot more about the distribution. So always important to calculate the moments of the distribution because they can give you a lot of great information and help you tell your distributions apart. So that's it. If you like this video, definitely check out the Deeplearning.ai specialization on mathematics for machine learning and data science. The specialization has 3 courses: linear algebra, calculus, and probability. And they're focused on what things on each discipline are used in machine learning. So the first course has vectors, matrices, linear transformations, determinant, rank, eigenvalues, eigenvectors, PCA, a lot of things. Because having a good understanding of linear algebra, matrix multiplication, vectors, etc. is very important if you're handling data. And I always like to see matrices as geometric things, linear transformations, etc., not so much as arrays of numbers, because there's a lot more intuition behind these graphical examples. The second course is on calculus, which is mostly optimization. There's derivatives, optimization, gradient descent, a lot of visualizations, because the idea is to understand how to maximize or minimize a function using calculus, which is what we do in machine learning when we minimize the loss functions in order to train models. And the last course is on probability and statistics. So it has things like Bayesian probability, probability distributions, like what we saw today. So this video today was a sampler of the third course. And then a lot of statistics like maximum likelihood, hypothesis testing, always with examples, because a solid understanding of probability statistics and a solid intuition is what you need to be a really successful data scientist. So definitely check out the course, and each one of the courses comes with a sampler video like this one, so you can find those in my channel and also in the links below. So thank you for your attention, and see you in the next video.